Okay, so the system bus is a pathway composed of cables and connectors used to carry the data between a computer microprocessor and the main memory. So as you all know, it is a pathway. That's why we call it as a bus, wherein you transfer the or carry the data between the processor and the memory. So basically, the bus provides communication path for data control signals moving between the major components of a computer system. These system buses operates on a contention basis. That means consider you have many what uh, components which requires a bus at a time. But so basically this bus system will provide the service based on the agreement basis, like maybe first come first serve, or it might be the priority basis. So based on that, you get the control over the bus. So only one is granted access to bus at a time. So at a time, only one component can access the bus. So effective bandwidth available is inversely proportional to the number of contending processors. So if you have multiple processors, then the bandwidth will be shared between those processors. Hence, the simple and low cost bus system is made out of 4 to 16 processors, made for 4 to 16 processor. So next, we will be studying about the backplane bus system. Okay, so this is a general specification of a bus system. So we are discussing about the backplane bus specification. So basically, this backplane bus interconnects the processors, data storage, and I/O devices. Okay, so this bus must be designed to allow communication between the devices on the bus without disturbing the internal activities or without interfering the working process. The timing protocols must be established to arbitrate among the multiple requests. You people know we are discussing about the buses wherein you transmit the data or you carry the data, right? So a timing protocol for the arbitration is very necessary. Okay, so then you have operational rules set to ensure orderly data transfer. Then signal lines are actually grouped into several buses. So we will see how exactly this backplane bus looks like. So this is the block diagram of the backplane bus, and at the side you can see the actual backplane bus frame. Okay, so as you can see, the backplane buses, as I said, the signal lines are grouped into several buses. Last line, as I said. So here they have grouped into 4 types of buses, that is data transfer bus, arbitration bus, interrupt and synchronization bus, and finally utility bus. Okay, so basically, as the name indicates, the first bus, that is data transfer bus, this it controls data, address, and control lines. Okay, so here the address lines are broadcast the data and the device address. So the number of address lines is proportional to the logarithm of size of the address space. So basically, the address lines, the number of address lines required will be always proportional to the log of size of address space. Okay, so if address space is of 64 bits, then log of 64 bits. So it will be like that. Then you have an address modifier lines which can be used to define the special addressing modes. Okay, next, the data lines are proportional to the memory word length. So word length of the memory is proportional to the data line is actually proportional to the memory word length. Then you have control lines which specify whether it is a read, write or timing or bus condition errors. Okay, so basically these control lines are used to indicate this, whether it is a read write operation, it is a timing control or a bus error conditions, all will be indicated by the uh, control lines. So as I said, the backplane bus has four different buses. They categorize the signal lines into four categories. One is data transfer bus. Next one is data transfer bus arbitration bus, interrupt and synchronization bus, and utility bus. So as I said, DTB is used for composed of data, address, and control lines. So address lines broadcast the data and the device address. So the number of lines are proportional to the log of address space size. There is an address modifier line which is used for the special addressing modes. Then you have data lines proportional to the memory word length. Then you have control lines which indicates the whether it is a read write, timing or bus error condition. Next one is bus arbitration and control. So arbitration means it is a process of assigning the control of DTB to the requester is called as arbitration. So consider one processor or one component is many components are requesting for a bus control, but one of it will get the control, right? That process, the process of assigning the control of the bus to a requester is called as arbitration. Okay, so there will be dedicated lines which are reserved to coordinate these arbitration process among the requesters. Okay, so a requester will be always called as a slave, whereas requester is called as a master, whereas receiving end is called as a slave. Okay, so here always requester will be called as master and receiving end will be called as slave. Okay, so now interrupt lines. So basically these interrupt lines are used to handle the interrupts. Okay, so there will be dedicated lines for synchronizing parallel activities among the processors. So it is done in the interrupt and synchronization bus. Next one is utility lines, which provides periodic timing and coordinate the power up and down sequences. Next you have a bus controller board which houses the control logic. Okay, so there will be a special controller board which is used to actually house a backplane control logic. So wherein you place all the logical components on it, which is called as a bus controller logic. Next, we will be studying the functional modules. Okay, so a functional module is a collection of elementary circuitry that resides on the one functional board. See here, functional modules reside here. In the CPU board, there will be a functional module, which is a collection of circuitry. Okay, so it works to achieve special bus control functions. Okay, so particularly you have a circuit, okay, on the CPU, which is used to control the bus functions. Okay, let us see what are all the functions it has. So first one is arbiter. Okay, so this is a functional module that accepts the bus request from the requester module and grants the controller control to one of the requester at a time. That is arbiter. As the name indicates, it is for arbitration. Okay, as I said, arbitration is a process wherein you grant the access to the uh, bus. You give the grant the access permission to the bus. So arbiter is a module which performs the arbitration. Next one is bus timer. So it measures the time each data transfer takes on the DTB, and it terminates the DTB cycle if the transfer takes too long. So basically, it measures the time taken for the data transfer, and if it takes too much time, then it will cancel the data DTB transfer cycle. Okay, the next one is interrupter. So basically, this interrupter module generates an interrupt request and provides the status information when the interrupt handler module requests it. So basically, it is to generate the interrupt request. Okay, next one is location monitor. So this is a functional module that monitors the data transfer over DTB. Okay, so power monitor monitors the power source and signals when the power becomes unstable. Next one is system clock driver. This is a module that provides a clock timing signal on the utility bus. So basically, the system clock driver provides a clock timing signal on the utility bus. Then you have board interface logic, which matches the signal line impedance, propagation time, and termination values. So this is very much needed in order to properly working of a bus. So basically, the physical limitations on these buses are due to electrical, mechanical, and packaging limitations. So because of this, only a limited number of boards can be plugged into a single backplane. So multiple backplane buses can be mounted on the same backplane chassis. Chassis is nothing but a frame. So on a single frame, you can have multiple backplane buses. So it is very difficult to scale a bus system due to the packaging constraint. These are all the limitations of bus system. So let me just brush it off. The bus system is a pathway composed of cables and connectors, and these are used to carry the data between the computer, microprocessor, main memory, or any other major components. So basically, we will be learning one bus system specification, that is backplane bus specification. So this interconnects the processors, data storage, and IO devices. So basically, this is how it looks like. This is a frame, backplane frame, wherein the backplane buses are installed. Okay, so now, as you can see here, this backplane signal system, backplane bus system is used to connect between the CPU, memory, and the IO devices. Okay, so basically the signal lines of backplanes are grouped into 4 different categories: DTB, arbitration bus, interrupt and synchronization bus, and utility bus. So basically, DTB is used for data address and control, comprises of data address and control lines. So arbitration bus is used for giving access to the buses. Actually, it is for arbitration purpose. As I said, arbitration is nothing but it is a process of assigning the control of DTB to a requester. So that job is done by the arbitration bus. Next, interruption and synchronization handled by interrupt and synchronization bus. Then you have utility bus. The functional module which is mounted in the CPU board has different functional controls, but control functions, which includes arbiter, bus timer, interrupter, location monitor, power monitor, system clock driver, and board interface logic, which does their own job. Okay, so the physical limitation, as I said, it is not scalable. It has restriction, a limitation on the number of boards. So on a single frame, you can mount multiple backplane buses. The next topic is addressing and timing protocol. So there are two types of integrated chips or printed circuit boards connected to a bus. Okay, so either active chips or passive. So there are two types of IC chips printed on the connected to the bus. Okay, so active devices like processors can act as a bus master or a slaves at a different times, but the passive devices like memories can act only as slaves. Okay, so memory by itself cannot operate anything, right? That's why they are called as passive, whereas the CPU processor can initiate any bus cycle, right? So that's why they are called as some masters. They can act as both masters and slaves at times. So as I said, only one can be in control at a time. So, but there will be multiple slaves that can respond. Understood? Then you have bus addressing. So the backplane bus is driven by a digital clock with a fixed cycle time, which is called as bus cycle. Okay, so there are few factors. These bus cycles are determined by few factors, that is electrical, mechanical, and package characteristics of the backplane. So basically, this bus cycle is purely dependent on how the bus is designed. Okay, so there are few factors which are affecting the bus delay. That is source line drivers, destination receivers, slot capacitance, line length, number of boards. All these affect the bus delay. Okay, so basically to optimize the performance, bus should reduce cycles on request handling, arbitration, addressing, and interrupts. Each device which participate will have the device number. So when the device number matches the contents of a higher ordered address line, the board is selected as a slave. So that is how you do the bus addressing. Okay, so basically the addressing allows the allocation of a logical device address under the control of a software. Okay, next is broadcast and a broadcal call. So most bus transaction has one slave master. So broad call operation, it is a operation where it is a read operation where multiple slaves place data on bus. That is broad call. Okay, whereas broadcast is write operation involving multiple operation. So basically a broad call is a read operation involving multiple slaves placing their data on the bus lines. Okay, so here special and or operations will be used, whereas broadcast is write operation involving multiple slaves. Okay, so when you're doing the broadcast, it is very important to maintain the coherence on the buses. So you should have a synchronizing, and there will be a timing protocol which is needed to synchronize the master and slave operations. As you can see in the diagram below, it shows the typical timing sequence when an information is transferred over a bus from source to destination. Okay, so first the master sends the request to bus is allocated, so it loads address and data on the bus. The slave is selected after the signal is stabilized, then signal data transfer. So the slave will have to take the stabilized data, then acknowledge the data taken. So if the data is taken, it will be known to the master, then it removes, like data is taken, remove the data and freeze the bus. So slave will get to know the data is removed, so signal transfer complete, it signals the transfer complete and freeze the bus. Then again the same repetition. So this is a typical time sequence for information transfer between a master and slave over a system bus. Okay, so first the master will send the signal, send the request to the bus, then the bus will be allocated, then it loads the address or data on the bus. So slave is selected after the signal is stabilized. Then it the master transfers the data signal, then the slave receives the data, then acknowledge the data taken. Knowing the data is taken, it removes the data from the bus. So knowing the data is removed from the bus, it sends the signal saying that the transfer is completed. Then the master can send the next bus request. So this is about the time sequence for the information transfer. Okay, the next one is synchronous timing. So all the bus transaction steps takes place at a fixed clock edges. So as you can see here in the diagram, this is a diagram which shows the synchronous bus timings with the fixed clock cycles. Okay, so the clock cycle time determined by the slowest on the bus. So here this particular diagram shows the equal clock, like fixed length clock signals. Okay, so here as you can see, all the transaction takes place in a synchronous way. So first data ready pulse will be sent by the master. As you can see, this is a data line. The first one is the data line. Okay, second one is data ready signal and data accept signal. As you can see, the data ready signal will be sent by the master, as you can see. So once the data ready pulse is initiated by the master, then the slave will send the data accept signal. Okay, so if the it is a synchronous bus. Basically, this synchronous bus is a simple structure wherein it is easy to control and it requires less control circuit. Thus, it costs less. So basically, the synchronous bus is suitable for connecting the devices having relatively same speed. So if you have relatively same speed, it is good to have a synchronous bus with the fixed time clock period. Otherwise, you can have asynchronous bus timing using what you can say, varying length cycle. Okay, so I think I will stop the class now.